here we say we optimize SVM classifier to avoid misclassification to clarify the data. If C is large, the margin of hyperplane is small. If C is small, the margin of hyperplane is large. So large C, chance of overfitting. If the C is too much, there could be chance of overfitting. Small C, there's chance of underfitting. But however, as I showed you before, just before this slide, it depends on the data set. That's why you have to always remember the statement, let the data speak. Now, so, but then generally, it's not always good to be greedy. Sometimes you have a data set that is not cooperating. You just want to force it to be in this side. You end up having a very bad system. But for sure, it's not all data that will be in this kind of form. Because this kind of data, ordinarily, if you treat your outlier, maybe it's an outlier. Because it is neither here nor here. This is a distinct class, actually. It's separated from everybody. So this is one of the importance of treating outlier. This is a kind of an outlier that will distort your system. Now, and that is why one of the opinion, kind of a new idea I'm proposing, hopefully once it gets implemented, you guys will see. And that is why we always try to use clustering algorithm before we use supervised learning, so that we can remove any data that is not good from our system before we continue. Now, we say the parameter controls the trade-off between the smooth decision boundary and classifying training points correctly. Still on C, we say if the C is large, then model choose small data point as a support vector. I will get the higher variance and lower bias, which may lead to the problem of overfitting. So as you increase your C, the system is getting closer to the point, so you might have the problem challenge of overfitting. So this is overfitting. Last C, you try to force everything to be. Some guys are supposed to make mistake. Draw a line here. Let this guy be mistake, but you don't want any mistake. You want everybody to belong. Then you might end up having an issue. And there could be, if it is too small, so you can have an overfitting. See, the model choose fewer data points as support vector and get lower variance, high bias, which is underfitting. So as we tell you, always be you be between the two. Don't go to overfitting, don't go to underfitting. And the best thing to do is always let the data speak for you. That is it. Do your parameter optimization, and then you'll be fine, inshallah. So C, control the trade-off between the achieving a low training error and low testing error. That is, which control the ability to generalize your classifier to unseen data. The lambda serves as a degree of importance that is given to misclassification. So the SVM poses the optimization problem, which look for maximizing the margin between both classes while minimizing the amount of misclassification. We want to maximize the margin, but we want to minimize misclassification. So that's why you are maximizing the margin, but you want it to get the minimum possible problem. For non-separable problem, in order to find the solution, the misclassification constraint must be relaxed, and this is done by setting dimension regularization to control how it solves things. Another parameter is the gamma. Technically, we said it is not an SVM parameter. It is a parameter of the kernel. One of the kernel, like RBF kernel. This is RBF kernel. RBF kernel has a gamma, which you must tune. You must find the value, the correct value of gamma for RBF if you are using it to get good results. So that's why some people say it's not compulsory. It is only when you are using RBF radial basis function and kernel, then it becomes compulsory to check for gamma. Now, so this is an idea of gamma. See, if you are using RBF, gamma will try to control how closer you are to it. Only nearby points are considered. But for this one, it considers even far away point in deciding. See, in low gamma, point far from plausible lines are considered, whereas in high gamma, point close to the plausible line are considered for classification. So this is how you control the effect of RBF. If the points that are closer, you want them to compare, then gamma will be high. But all along, like I said, this is our theory. The practical is go on your data, start checking the value of gamma, look for the acceptable range, search for it, and then try to get the best one that works for your data. So nobody can really say use low or use high. See? Yeah. So we said the value of gamma and C should not be very high because it leads to overfitting, or it shouldn't be very small due to underfitting. The question is, what is small? What is high? These are all relative terms, Shabab. So we need to choose the optimal value of C and gamma in order to get good fit. Yeah, but how do you get the optimal value? By doing parameter search optimization. This is what I introduce for my student. I usually try, it's very, very important, hyperparameter optimization. So you just go to literature. They say we go read about literature. They said C is good to be 20. I said, this is not correct. It depends on your data. 20 people might have used C to be 20 and it's working for them. Your data might not work with C is equal to 20. The best way to set up the parameter optimization, have your plot, get the best value for you, you are good to go. The insensitive loss function, which we call the epsilon, it's another one also. Epsilon is actually part of the hyperparameter. It had an effect on the smoothness of the SVM response. It also controls the number of support vector. So in which case, both the complexity and the generalization capability of network depend on this value. So not as important as C and kernel. The most important is kernel, after that C, after that epsilon and other classification. So you just need to play with whatever parameters available and try to get the optimal value before you move on. Now, towards the end of the course of support vector machine, what about multi-class SVM, Shabab? It's very, very important. Pay attention, Shabab. What about multi-class SVM? You want to solve a multi-class problem. You want to predict if a student is going to get A plus, B plus. Unfortunately, support vector machine does not have a definitive multi-class SVM formulation. Unfortunately, this is a drawback because it only works on the principle of drawing a line. So when I have three different classes, how do you draw a line between three different classes? It's not possible. So this is why. How does it do it? So in practice, we have to obtain a multi-class SVM by combining multiple two-class SVM. How do we solve the problem? So if I want to solve a problem for A, B, C, support vector machine cannot do it. Decision tree can do it. Other methods can do it. But for support vector machine, it always draw a line between two classes. So I have to break these three classes into two. I have to do AB, AC, BD. I'll solve this as a one, solve it separately, solve it separately. There are two ways of implementing multi-class SVM. Pay attention, Shabab. Everybody should be able to stay this. This is very, very important, please. There are two ways of doing multi-class SVM. The first one is called one versus others. Here you learn SVM for each class versus others. Testing, apply each SVM to test example and assign to the class that return the highest decision value. What do we see here? Let's say we have A, B, C, D. This one is saying you are going to train one SVM A against B, C, D. It means you change all the label for all this data, you change them to become class. You say this is class 1. You change all this data to class B, class 2. All of them, B, D, C. They are different classes, but you treat them as class 1, another class. So you are going to train one SVM to separate A from BDC. Then you train another SVM to separate B from ACD. You train another one to separate C from BAD. And then you train another one to separate D from ABC. It's one versus one. Pay attention. One against one. You learn an SVM for each pair of classes and testing each learn model. You vote for a class to assign to the test example. This is the one we are talking about. I have A, B, C. Pay attention, Shabab. The previous one, I'm training A against BC. No, we don't do it now for this. One versus one. Me and you only. So you give me, you merge us together. I'm going to train A and B. This one SVM. I'm going to train another SVM A and C. I'm going to train another SVM B and C. A, B, A, C, B, C. Halas. I'm going to train 3 SVM for this. And then I'm going to, when I have a new sample, I'm going to send them to it and I'm going to vote for the class to assign the test sample to. This is called one versus one. This is the indirect way of solving the problem of multi-class problem in SVM. See, that's why a big research to be done is, should I use one against one versus one or one against all? Which one is better? Nobody can tell. Your data will have to speak. See, your data will have to speak. Which one should I use? So this is the multi-class, one versus others. You can see this is the idea. You see, this is the classes: normal, abnormal, broad, high, medium, and low. So you classify normal here, this normal class. You move to the next class. See, you train another SVM again. This guy is out. You train the remaining one against all. You take one out again. See, you separate it from others. These ones are becoming one. You keep doing that until you finish everything. So one against all. This is one versus others. That is for SVM. The second one is one versus one. You can see I train C1 and C2. I draw a separating upper plane between them. Again, C1 and C3. I draw another one. And then C3 and C2 and C3. I do another one. So at the end of the day, I'm going to have a way of voting. When I have a new test sample, okay, we can try to see which one are we going to classify it on. This is how we use multi-class SVM. Now, so what are the challenges of SVM? What are the advantages of SVM? We said it works really well with clear margin of separation. It is effective in high dimensional space. See, it is effective in case where number of dimensions is greater than the number of samples. Pay attention to this above. This is a unique, super advantage of SVM. It is effective in cases where number of dimensions is greater than the number of samples. See, we have 25 features and you have only 20 samples. Support vector machine will still get to reasonable results. No other machine learning algorithm, as far as I know, has the capability. So when you have very high huge dimension, number of features are many, you have support vector machine still performing excellently well for you. So let's pay attention. This is very, very important, a very unique attribute of SVM. When you have number of features that is more than the number of classes, the problem you are having is going to lead to cost of dimensionality. That's that problem. So you need more sample and the sample is not available. So you're having problem of cost of dimensionality. And the feature selection might assist you, but support vector machine is able to do some stuff. Now, it uses a subset of training points in the decision function, which we call support vectors, so it is also memory efficient. So once we train, we do the training of our model, all the other samples from the training set, we throw it away. We only take the support vectors. This is an advantage in support vector machine. Once we finish training, we don't need all those samples for training. We only need the support vectors. Unlike other systems, you still need to keep the training sets to guide you when you're going to do testing. But for support vectors, once you finish training, it's only going to deal with support vectors. Other stuffs are gone. So this is an advantage to it. So SVM is, there are many publicly available SVM packages. You can see kernel machine. So it's a very powerful, lot of work going on support vector machine. I personally like it because when I face a lot of challenges with my data, I go for support vector machine, and mashallah, alhamdulillah, has been assisting me a lot. But don't say, I'm not saying it's going to work for you in all situations, okay? I didn't say that. That is against the principle of machine learning. Kernel-based framework is very powerful and then flexible. And the SVMs work very well in practice, even with very small training sample. This is another very unique attribute. Even when your training sample is very small, SVM will be the best alternative for you to go for. Now, what are the challenges? We say it doesn't perform well when we have large data set because the required training time is higher. So for support vector machine, when your data is huge, it's going to take a lot of time because it has to compute. Actually, one of the disadvantages is that it needs to compute the matrix of kernel for every pair of example. This is what we are saying here. During training time, SVM must compute the matrix of kernel value for every pair of example. Can you imagine? So every value you have, every sample you have, then you have to compute the transformation kernel for it. Imagine I'm having 1 million samples. So I'm going to generate another another different data from the kernel for every sample. So therefore, SVM is computationally intensive and also consume a lot of memory. See, this is why they often refer to it as because of the number of data is going to imagine having several kernel. I have 1 million samples. I have to generate another 1 million kernel matrix also again to represent the conversion from lower space to the higher space. So then another problem with SVM is there's no direct multi-class SVM. You need to combine 2 class SVMs to solve the problem, like we just discussed now. It's a disadvantage of SVM. It's one of the negative side of it. So that is why in life, you might not be able to get anything that is perfect. See, somebody said that someone was looking for a village that is perfect. Somebody on knowledge now told him, if there is a village that is perfect, the moment you as human being enter that village becomes imperfect because you're already inside that village. To tell you that nothing is perfect. You get my point? We are not perfect as human beings, so which means we need to try to accept some of our mistakes, some of our laxity, and try to put ourselves right. So as powerful as SVM, you can see how many challenges it has. The learning can take a very long time. So for large-scale problem, if you have a very big data, the support vector machine might not be an option for you because you can stay there till tomorrow. It will never finish. But for very small data samples, wow, this is a strong point from this is a question. Because SVM, when you have high dimensional data that has a lot of sample, maybe a company invites you to Khobar, to the Jubail, that they want to develop a machine learning, but they're having problem because there are so many features, but few samples. What do you recommend for me? You see, we recommend support vector for you. But what is the problem we are facing? The problem you are facing is cost of dimensionality. Pay attention to that. That problem they are facing is cost of dimensionality. The features are more than the samples. Because for every sample, you need 10 raised to the power something of the number of samples. But now they don't have samples. The solution is feature selection. But when they after our issue of feature selection does not solve the problem, they gave you neural network and support vector machine, you go for support vector machine because support vector machine has that capability to perform in the face of high dimensional data. We said the complexity of trained classifier is characterized by the number of support vectors rather than the dimensionality of the data. He said the secret for this support vector machine is that after the training, the system is not going to be dealing with all the training examples. It's going to select only the support vectors, which are usually few. You can see before that we got 1 from one side and 2 from the other side. Imagine having 1 million data and you have like maybe 10 or 15 support vectors. And this is what you're going to use for the testing set. This is one unique way. The support vectors are the essential or critical training examples. They lie closer to the decision boundary. Once you determine the support vectors, you don't need other training sets again. You can throw them away because the support vector, they are the one closest to the decision boundary. Anybody that falls closer to the support vector, it belongs to that class. If you fall to that support vector, you belong to this class. It means with the support vector, we can successfully classify new incoming samples without recursing to our training examples later. If all the training examples are removed and the training is repeated, the same separating hyperplane will be found. You see? So this is our support vector machine is so unique. Now, the number of support vectors found can be used to compute an upper bound on the expected error rate, which is independent of data dimensionality. Therefore, an SVM with a small number of support vectors can have good generalization even when the dimensionality of data is high. This is the secret of support vector machine, Chaba. Why even though very few samples that you don't expect anything to work, it still works. But once it train and establish the support vectors, it will use that support vector to classify the new unseen sample. And this is the capability that other methods didn't have. To date, I can say the method that worked for me most has always been support vector machine. But then I'm still short of saying it's the best. Nobody say that in machine learning. But as far as I'm concerned, whenever I have tough data, I go for support vector machine. And it has always performed. Application of SVM. Say SVM has been used successfully in many real-world problems: text, image, bioinformatics, handreading, and whatever value. Key points. You say use optimization to find solution, which is appropriate with few errors. Seek large margins separating to improve generalization. Use scanner trick, see, to make large feature space computationally efficient. A support vector machine allows you to classify data that is linearly separable and that is linearly inseparable. If it is not linearly separable, you can use the scanner trick to make it work. The scanner trick will always make it to become linearly separable. And SVM correctly classify the training data. It will generalize better with unseen data, and it doesn't suffer from the cost of dimensionality, which is a problem. If a company invites you and they say they're having a problem of so many features but few samples, just quickly know that the problem they're having is cost of dimensionality. Cost of dimensionality. We discussed this under feature selection. And the solution to that problem is feature selection. Now, well, if somebody asks you, which machine learning algorithm will you use in this kind of situation with so many features but few samples, then support vector machine should come to your mind immediately. Support vector machine should come to your mind as a possible classifier. But if somebody asks you, what do we call that problem, where there are so many features for few samples, that is going to lead to cost of dimensionality. The more the feature, the more the sample you need, but then the samples are not available. And the solution is to go for feature selection to bring it down. I hope that is clear, Shabab. So this is what we are going to have it on support.